All right, we're going to look at the solutions to a very particular kind of differential equation called a separable equation. And the first thing we're going to do is just get to the idea of the chain rule, then try to identify what is a separable equation, and then using this idea to solve. So the idea that we're going to first start off with is the chain rule. And just as an example, suppose I have this integral, the integral of 1 plus log of t times 1 over t dt. And if we wanted to try to solve this integral or find this integral, then we would do a u substitution. The reason we want to do the u substitution is because the derivative of 1 plus log of t is 1 over t dt, and we can see that there. So let's go through and do the whole thing. So if I have the integral of 1 plus log of t times 1 over t dt, then to solve this thing, I'm going to notice that the derivative of this thing is right there. So I'm going to say let u equal 1 plus log of t. And now if I take the derivative of that thing, and that becomes the derivative of 1 plus the derivative of log of t, and derivative of 1 is 0. So I just have 1 over t. And because this thing right there I can see there means then, in terms of the notation, I can think of this as du is 1 over t dt. So this integral, 1 plus log of t times 1 over t dt, is the same thing as looking at, well, there's u, there's du. So I'm going to get 1/2 u squared plus c. And now, going back to my definition of u, that's 1/2 1 plus log of t squared plus a constant. And I can check my work here. So what did we just said? We said that integral of 1 plus log of t, 1 over t dt, we claim is 1/2 the quantity 1 plus log of t squared plus c. Now if I check this, if I take the derivative of this thing, I should get the original integrand. So if I take the derivative of that, well, I've got the derivative of something squared, so by the chain rule, I can just forget about this constant here that I'm multiplying. I'm going to have 2 times the something times the derivative of the something. And don't forget, I've got the derivative of a constant, which is 0. But we already said that this is 1 over t, so the 1/2 times 2 is 1. I get 1 plus log of t times 1 over t. And lo and behold, that is the same thing as what I have there. So that is the antiderivative. Okay. Let me do this and look at it a slightly different way. So we started off with this thing, right? What if I said y was 1 plus log of t? Does it change anything? Well, dy is just going to be the derivative of 1 plus log of t, which is 1 over t dt. So this becomes the integral of y dy, and that's 1/2 y squared plus c. So it's basically exactly the same thing. There's no difference, right? And my y, I already said, is 1 plus log of t squared plus c. What's important? The important is the chain rule. Chain rule says that the derivative of some function of y, and here I'm assuming y is a function of time, is going to be the derivative of f times the derivative of y. Again, that's just the chain rule. And this relationship here says that if I take the antiderivative of f prime of y times y prime with respect to t, that's just f of y. And again, I have to be careful and could be off by a constant. So the antiderivative is just undoing this derivative. And this notation here, we call that dy just as a placeholder to help our notation and figure out what things are happening. So what's important is that if I have the integral of something times y prime dt, I can really just focus on this thing and think of that as trying to find the antiderivative of that f. So let's look at an example of what this means. Suppose I have y prime equals 2 times y. Again, y I'm just going to assume is a function of t, just because that's what I'm used to. And this is my original equation, is y prime equals 2y. And what the question is asking is, I want to find a function, y of t, so that when I take the derivative of y of t, it's the same thing as taking 2 times the original function. Okay? So a differential equation is about trying to find a function. When I take its derivative and plug it back into here, everything's going to work out. Left-hand side is going to equal the right-hand side. In this case, though, notice I can perform some algebraic steps and I can get y's on the left and t's on the right. If I can do that, we're going to say that the function is separable. So what do we have? We have y prime equals 2 times y. I'm going to multiply both sides by 1 over y. And if I do that, well, I'm just going to have 1 over y, y prime, then the y's cancel on the right, and I've got 2. So again, I only have things that involve y on the left, and on the right, I can think of this as only t. In this case, it's just a constant, so it's basically anything that doesn't have a y is what's on the right. So I can focus on what does that mean. So I'm looking for the derivative of some function so that I get 1 over y times y prime. Okay, so again, we started off with y prime equals 2y. We divided y from both sides, and I got that. Because of the chain rule, what do I say? The chain rule is that the derivative of f of y is f prime of y times y prime. Notice there's my y prime, and there's a y prime. So I want to find something whose derivative is 1 over the thing I give it. And what is that? Well, notice the derivative of log of t is 1 over t. So that means that the derivative of log of y is going to be 1 over the thing I give it, but by the chain rule, it's going to be times y prime. Again, we're assuming that y is a function of time. Let me go through and do this in a more mathematical way or more technically correct way. So what do I have? I had y prime equals 2y. This function is separable, or I should say this equation is separable, because I can get all the y's on one side and everything else on the right. I can take an antiderivative of both sides. Oops, antiderivative with respect to t. This thing is like looking at 1 over y dy. And so that's just going to be the log of y. And then the right-hand side is 2t, because it's the antiderivative of t, or sorry, 2. Now I got to be careful. Whenever I do an antiderivative, I'm going to be off by a constant, so I've had to add a plus c. Technically, I should have a plus c on the left as well as the right, but they're two different constants. So if I subtract one to the other side, I'm just off by one constant. So what do we have now? We now have, right, we started off with y prime equals 2y, 1 over y prime is 2. Take the derivatives of both sides, and I have the antiderivative of 1 over y is log of y, antiderivative of 2 is 2t plus c. What was my original goal? My original goal was to figure out what's going on with y as a function of t. So I need to isolate that thing. If I take the exponential of both sides, then e to the log of y is y. That's just because they're inverses of one another. So I have that. That is a solution to the differential equation. And notice there's a constant here. I'm going to have to find out some other ways if I'm asked for a specific solution. But this is going to give me my general solution. Okay, this is correct and it's fine. If you look in the book and you look at a lot of other sources, they do not leave it like this. And the reason they do not leave it like this is that when we go to actually try to figure out what the C is, it can be a little complicated. So I'm going to take a few more steps in this particular case. I'm going to notice that e to the 2t plus c is the same as e to the t times e to the c. And again, c is a constant, which means that e to the c is a constant. So I'm just going to arbitrarily define a new constant called k to be e to the c. And if I do that, y is k times e to the 2t. So a solution is going to look like that. All right. So now, just be a little bit careful here. I want to note that right, we started with this thing. We're looking for y of t. Where did that constant come from? Oops. So I divided both sides by y to get this. When I did the antiderivative at this step, after I did the antiderivatives, I had the constants here. And I ended up with log of y plus c1 is 2t plus c2. And I kind of worked behind the scenes here to subtract those two constants. And I just called that c. You need to be really careful about where this constant comes from. It comes in this step right here when I do the antiderivative. And remember, our final answer looked like that. And there was no plus c. Okay? So you can't just work through and do this and throw a plus c at the end. If you do that, you'll get something that's not correct. Now, by the way, I can do a quick check here to see if is this correct. So my original equation is y prime equals 2y. I claim that y equals ke to the 2t. So let's see. If I look at the left-hand side, y prime is going to be the derivative of ke to the 2t. I can just pull the constant out, take the derivative of e to the 2t. That's going to be e to the 2t times the derivative of 2t is 2. On the right-hand side, 2 times y is 2 times ke to the 2t. Left-hand side is equal to the right-hand side, and life is good. Okay, so just a quick recap. We're looking at a very specific case here where we have separable equations. I did not formally define that, so let's do that now. An equation is separable if we can express it as y prime equals some function of y times some function of g. Okay, so in the previous example, we had y prime was 2 times y, f of y was just y, and g of t was 2. And the reason this is so important and so nice is that I can divide both sides by f of y to get that, and now I can just integrate both sides, and I can just bring all my Calc 2 powers to bear on that thing and work solely with that.